Hello. So today we are going to be starting our conversation on energy balances. So the major idea with energy balance is simply like mass balance, just trying to figure out where energy is coming from and where it's going. And the big guiding principle here is going to be our good old friend, the first law of thermodynamics. Can't create or destroy energy, just move it around in pools. So we've got a lot of the same advantages we do with material balance. And a lot of these concepts should be fairly familiar from physical chemistry, but one of the things you need to watch out for is that chemical engineers and industrial chemists tend to have some slightly different terminology to watch out for. So let's go ahead and start overviewing our systems. So one of the big things to remember is why we should care about energy. And then one of the biggest reasons why is, um, as we've seen in distillations, a lot of chemical processes require a whole bunch of energy, and that actually turns out to be uh, one of the major costs. So being able to monitor the energy is going to be really important. But then this leads us to the second question. What kind of energy does a chemical system have? So this is going to be the same sort of things you've covered in other chemistry classes, just with slightly different terminology. So the first of which is going to be potential energy. So this is essentially due to the position of the system in some sort of potential field. So the big ones here are going to be gravitational energy, electrical energy, and magnetic energy. So where I've trapped my system in a gravitational, electric, or magnetic field. So this is less about what energy a system can potentially do, and much more about what sort of energy is embedded by the position of the system. Then we have our good old friend, kinetic energy. So this is essentially just the energy due to translational or rotational motion. We typically leave vibrational motion uh, out of this category, though some people will include it. And so again, this is going to be most of our energy forms of movement. So this is both the kinetic energy of the system moving as a whole. So for example, flowing air, but this is also just the embedded kinetic energy due to random motion, AKA temperature. Then pretty much everything else is going to be embedded into internal energy. And the biggest contributor here is going to be chemical bonds, whether this is intramolecular bonds, so covalent bonds and ionic bonds, or whether it's simply intermolecular forces like hydrogen bonds or van der Waals forces. So these are going to be our major energy pools that we're going to be talking about. The other major feature, we have to address is essentially how can the energy move and change? Because just because energy starts in a chemical bond doesn't mean I can't break that bond and turn it into potential or kinetic energy. So when we're looking at at the movement of energy, one of the biggest ways that we move around a lot of energy is going to be by carrying it in the molecules themselves. Because if I move, say, a kilogram of hot steam from one place to another, say across a room, then it turns out that I moved a lot of energy in that substance. So when I move substance from one place to another, there's all that energy caught up in the bonds that's also moved. And this is one that we typically don't think about a lot. Next major one that we've addressed in some previous classes is this idea of heat. So this is essentially thermal energy. So this is going to be things such as the random kinetic movement of molecules, which we typically think of as temperature. And heat is specifically the movement of that energy based on temperature differences. So the fact of I have two molecules colliding together, energy is almost always translated from the hot molecule to the cold molecule. And so that's how we typically tend to see thermal energy move in a heat format. This will not include energy that moves, say, based on the movement of hot molecules. And then finally, we have work. So this is a general catch-all term for anything else. So this can be, say, pushing a turbine, gas expansion, electrical current. So any chemoelectrics are going to end up being here. This can even be things like magnetic work. So if I'm actually physically moving an external object, this is typically going to be energy leaving the system as work. This is often one that we're very concerned with in engineering. Though that said, maybe it's not the most common form. The most common form is generally actually going to be the movement of molecules. After that, we typically see a lot of temperature differences. So heat is almost always going to occur whenever we have work. So these are pretty typically listed in terms of their frequency, if if not their importance in what we want out of the system. So these are going to be essentially the types of energy and how it's transferred, but this is going to be slightly different from another important feature, which is the types of changes in energy. So how can the energy inside a system increase or decrease? Because if I moved energy out of the system in heat, through movement, or in or by work, I must have driven some type of energy change within the system of itself. So one of the most important is going to be the change in internal energy. Note this is not the change of potential energy, but this is again typically going to refer to the change in the bonds of the system, or essentially of molecules entering or leaving the system. So this is usually going to indicate a type of change in the chemical bonds, either through bonds breaking or forming, or because I have bonds entering or leaving the system itself. Next up, we have our good old friend, the change in kinetic energy. So this is going to include most types of temperature transfer. So this is going to occur very frequently anytime we see the temperature increase or decrease in the system. And then the last one, which we're going to not talk quite as much about, is changes in potential energy. Say if I end up driving a fluid up or down a pipe. At that point, I'm going to see some change uh, in the gravitational energy of the system. However, due to the shortness of the class, we're going to be talking about this one a little less frequently. And again, we can characterize how this energy happens by looking at the heat put into the system. So again, one of the things to watch out for is there is some slightly different terminology and notations in industrial chemistry. So in this case, just like in chemistry, a positive heat value indicates that energy is flowing into the system. However, when we're talking about work, work is always going to be represented by the work done by the system, because this is what really matters from an engineering perspective. So in this case, a positive value indicates that energy is leaving the system. So we do have a sign flip from the notation that we encountered in physical and general chemistry. Now we have all of these basic terms built up. What we're going to be doing is essentially making use of our good old friend, first law of thermodynamics. So all of these energy ways that the energy can change have to end up adding up. So, so any change in the internal energy, the kinetic energy or the potential energy, so this is energy in the system, has to end up equaling the amount of energy entering the system through work or heat. So if I have an increase in energy in the system, it will either be indicated by bonds, movement, or some sort of change with regard to a potential field. And energy can only enter, or it will typically enter or leave the system by work or heat. So let's go ahead and take a look at, say, I have a gas flowing down a pipe. It may see an increase in energy of the system. For example, the molecules leaving this end of the pipe may have a higher temperature, or they may have more stable bonds. In this case, energy had to come into the system somehow. A very typical method is going to be as heat, but it may also end up entering as work. So using this, we have our general equation for energy balance, also known as pretty much a equation of the first law of thermodynamics for all our various components. However, we've got 5 terms, and we might want to simplify this. In general, we're going to find that changes in the kinetic energy might be a minor contributor, and changes in potential energy typically end up being very minor. So if we make these approximations, then I get the change in internal energy is equal to work minus heat. And then we can make a classic approximation from physical chemistry and assume that almost all of our work is going to be PV work, so expansion or compression of the system. So if we do this, we can end up dropping our equation to our old friend from PChem. Change in internal energy is heat plus PV, or our heat is going to be our change in internal energy minus PV, which turns out is the same thing as enthalpy. So we're going to be typically making use of an enthalpy metric, which is going to be much more heat-based, and I am able to better ignore any changes of PV work because it's annoying to keep track of in large systems. So what we're going to be doing is typically to track the heat entering and leaving the system, we're going to be focusing almost exclusively on the change in enthalpy. So if I'm looking at change in enthalpy of the system, it's going to occur in generally 3 major ways. Each is associated with a different label or type of heat. So the first of which is sensible heat. So this is going to be the heat or the energy required to change the temperature of a system. We call this sensible because I can feel the temperature change. And my sensible heat is going to be related to the temperature change by the heat capacity. So again, the heat capacity is going to be the specific heat capacity of the system as a whole, or the chemical that I'm looking at specifically. And so again, this is the major reason why heat must be added or added to raise the temperature system, or I can cool the system by removing heat. So again, when we're talking about temperature change, I'm going to be typically referring to this as sensible heat. So if I'm looking at how the sensible heat in a system changes, let's go ahead and take a look at a much more industrial chemistry sort of question, rather than a typical chemistry question we've dealt with in the past. So I've got an ethanol plant where I need to end up heating a 10 kilogram per minute stream of 12% by weight ethanol. So this is essentially a strong beer. So I need to raise that from room temperature to 96 degrees C before I feed it into a distillation column, because turns out, and of course, in this problem, I feel like making some distilled spirits. So one of the things to make note of in this problem is I've got 2 different components. So I'm going to need to include a little bit of mass balance along the way. So I need to figure out how much heat needs to be added to the system. So first thing we're going to want to focus in on is my temperature difference. Then I need to figure out the moles of each of my component. So I've got 10,000 grams per minute, 10,000 grams per minute, and about and a 12% mixture by weight. So 12% of that mass is going to be my ethanol, and then the molecular weight of ethanol itself. Running through that conversion, I've got a feed rate of about 26 moles per minute. And we can use this same process and then to figure out the enthalpy of the system, the change in enthalpy of the system, I can take my moles per minute and multiply it by the heat capacity of the ethanol times the temperature difference. So Cp times times moles times delta T gives me essentially a change, an enthalpy flux of 208 kilojoules per minute. So a good way to look at this is that I have to, in order to accomplish this heating, I need to be adding in 208 kilojoules per minute. And one of the things to watch out for is we've typically done heat transfers before in a batch sort of system. In this case, I've got a flow through system. So I've got to worry about the actual rate of movement of my chemical, which results in a rate of heating. And we can do the same process for water. Well, I'm first going to determine the amount of water in the system. Turns out to be a whole lot more because water is lighter and is the majority component. So we have almost 500 moles per minute of water traveling through the system, which ends up meaning that I need to add almost a little over 2.5 megajoules of energy per minute. So this is a whole lot of energy. So my total heat that needs to be added to the system is a little bit under 3 megajoules per minute. So if I was actually going to be trying to perform this heating in the real world, at current energy cost, this ends up being about 8 cents a minute to drive the reaction, or I'd have to pay about $113 per day to just drive this process forward. So one of the useful things about kind of bringing all of this stuff together is you can turn some of these heating processes into actual realizable costs. Now, one of the things that you should always be aware of when dealing with these heat capacities is that heat capacities typically only going to be constant for relatively small temperature changes. So this is our good old friend Kirchhoff's law, where we can really only consider heat capacities constant for temperature changes of less than 100 Kelvin. Turns out that changes of greater than 100 Kelvin are pretty common in industrial chemistry, where I may need to heat a feed system 200 or 300 or even 500 degrees. So how can I go ahead and deal with this? Well, turns out we have to make use of our good old friend linear expansion. So one of the things to watch out for is that almost every resource you will consult will use a slightly different form of the linear expansion. But this is a fairly common one in the NIST standard books. And using this, we can insert into our good old friend, the Kirchhoff equation, where the change in enthalpy is related to heat capacity times the change in temperature. And then we essentially do an integration about the system and get our net enthalpy change equation with a polynomial dependence on the temperature of the system. However, turns out there's going to be several other approaches. One of the biggest things that's worth noting is that you can use other fitted models if you have a sufficient amount of information already present, or this one's becoming much more common with greater computational resources. There's a lot of pre-built computer models out there that you can make use of. So again, one of the things to watch out for is that everybody likes using a slightly different set of equations for these large temperature changes. So make sure that you're consulting the resource that you're using and making sure you're using the right model. Now, all of this was just with regard to sensible heat. So this is heat that ends up with temperature changes that I can actually feel. But don't forget, a lot of times what we're caring about is latent heat. So this is essentially the heat required to cause a change in matter. So this is essentially our good old friends melting and evaporation, but we also have their cousins, condensation and freezing. So if I want to figure out the change in latent heat, I'm going to use good old equation. Heat is simply going to be equal to the moles times the molar enthalpy of vaporization. One of the things you need to make sure you watch out for, a lot of our enthalpies of vaporization and fusion are going to be given as size intensive properties or molar properties. And heat is a size extensive property. So always make sure you keep track of exactly what you're heating and how much of it is you have. This ends up becoming a very important feature. So when we're trying to calculate these heats, one of the big things to watch out for is that a lot of the enthalpies you're going to be finding in tables are only for a very specific temperature, say room temperature or the melting or boiling point. So you'll need to correct for, do any corrections if you're trying to figure out the enthalpies of vaporization for any other temperature. So one of the big things to make note is that you're often going to have to address latent heats when solving real problems, because it turns out one of the big things we're trying to drive in a lot of chemical processes are going to be phase changes. So let's go ahead and look at an example system. So if I will have a reactor that I'm going to heat by condensing steam. So I'm going to put in high temperature steam, and then I'm going to end up with a water stream coming off. Well, if I'm going from steam to water, that means I lost energy. And that lost energy is going to go into heating my reactor. So I want to figure out, if I'm driving through about 100 kilograms per steam per hour, how much heat am I putting into the reactor itself? So for that, we need the enthalpy of vaporization of water, which is about 40 kilojoules per mole. And then the rest is unit conversion. So I can convert my kilograms of steam to moles of steam, and then to the energy put into the system. So I've got a negative energy because energy is leaving the water to enter the reactor, and I'm providing about a little over 200 megajoules per hour. So a fair bit of energy just by adding in a fairly reasonable amount of steam. So this is a very common procedure in a real industrial system. So next time, we're going to be looking at how we can start using these basic principles of physical chemistry and applying them more specifically to industrial systems. Till then, take care.